All right, hello and welcome to the Off by One security stream. Thank you for joining us this week. I've got a very special guest, Connor McGarr, with us this week, who is going to talk about some amazing kernel exploitation stuff. And this is a topic very near and dear to my heart as well. And I've been teaching it for many years in the SANS course, Sec 760. And I'll talk briefly about the history there and kind of where it got up to. And then Connor and I have a lot of stuff kind of want to go back and forth on. If you have questions yourself, please do pop them in the chat. Know that the chat is a little bit delayed, so it might take us a moment to respond back. Don't think we're ignoring you. We'll definitely grab your comment before it gets too late. But let me first get started here by just saying quickly again, thanks for coming to the stream. As you know, if you've watched this before, the goal here with this stream was to have it where we focus on more advanced topics and techniques and tools. There are a ton of great streams out there already covering the introductory stuff with regard to exploit development and just anything in the offensive space. And just to point out on that note as well, I had some people saying, hey, are your topics always going to be like really advanced stuff? We just recently have talked about red teaming, and we talked about some crypto topics, and also it won't always be super advanced, but that was kind of the intention though with this stream, was to make it to kind of cover areas that aren't as widely covered as some of the other ones, like the more introductory topics around buffer overflows and stuff, like I said. So just a quick note, a couple streams ago, I talked about like what the golden era of exploit development was and hacking was. And I mentioned like the 90s and the early 2000s. And I mentioned a left one smashing a stack for fun and profit and those well-known papers and techniques that were released by like Solar Designer with Return to libc and the whole heap spraying technique from Skyline back in 2005. So back then, there were like hardly any, if any, mitigations at all on the operating systems. And so until Windows XP Service Pack 2 came out, there was nothing. There was no DEP, no ASLR, nothing. And so if you found a vulnerability, it was just super easy to go and exploit it. I remember mentioning like MS03026 was one of the first modules on Metasploit. That was the blaster vulnerability, the MSRPC decom bug. And you could just point it at a system and pop a shell with no effort needed at all. And then over the years, these mitigations start dropping on, and you've heard us talk about those millions of times before. Some of the more challenging ones to get around, like control flow guard, address space layout randomization, depending on whether or not you have a memory leak, just all kinds of factors. But those are still kind of seen as relatively, I guess you could say, it's realistic. It's possible to get around those mitigations if the conditions are right. As we move on, and what we're going to cover primarily in this stream, you get into the kernel on modern Windows 10, Windows 11, and then the server operating systems. You really get into the space where we've got virtualization-based security, so VBS. This is where you might have a secure kernel instance, and then you've got these isolated user mode processes running where LSAS used to run in user mode on the regular system. It's still there, but it's pretty much empty. And then there's this other process called LSAIO or something like that that runs as an IUM on the secure instance. And to get over to it, you've got to go through like a broker service that's kind of, well, it's well hardened. And even if you're using WinDebug to debug the kernel on the one side, you can't just shift over and debug the secure kernel. So being able to do that is just very, it's good. It's, as we move forward into that, and that's some of the stuff I want to talk about with Connor here, it's making it just really, really hard. And the days of the techniques where there were these techniques you could use, like always overwriting the HAL dispatch table +4, always stealing PID number 4's token by walking the AP links, and those techniques, some of them are still possible, but they're even starting to go away. And as we get to that point further and further, really all we're left with is occasional read-write primitive opportunities. Remote code execution becomes very challenging. And Connor's going to talk a bit about HVCI, which is another big painful one there as well. So with that being said, I will just go ahead and let Connor introduce himself here, who's been doing some amazing work in the kernel space.
Yeah, thanks, Steve. So as Steve mentioned, my name's Connor. Pretty much just interested in anything exploitation related, vulnerability research, programming in C, the best programming language. In my work day to day, I work at CrowdStrike. I work on the sensor. So looking at tradecraft today, what's happening, what kind of techniques are being used, doing research on that, and actually extending the sensor itself to try to detect those sort of things. Prior to that, I worked in the red team at CrowdStrike, the customer facing red team, which we have one if Many people are kind of shocked by that, but we do have a customer-facing only red team, and did that for about 2 years. Been in the industry since about 2019. I'm definitely a young one. And yeah, pretty much just like anything offensive related, and super glad to be here.
I think that's so. You ended up there with something that leads into a great question, which is you said you started in 2019, which is as the work that you're doing now, only having like 3 years there is pretty amazing. Most people, it takes a long time, if ever, to get up to that point. So I get that question a lot where people say, well, if I want to get into hacking Windows 10 and Windows 11 and modern applications like browsers and all, or even the kernel, should I start from the beginning and understand like basic buffer overflows and kind of work my way up, or is there an easier path? What do you think?
Yeah, I think that this is actually a great topic because this came up yesterday in a Discord server that I'm in. We often hear with like basic buffer overflows, right? You hear the term thrown around like, "Oh, we've overwritten EIP, the extended instruction pointer." Yes, that is true. The contents of EIP you can control, but EIP is not, it's a fixed CPU register. It's not something that you directly override. And when you get into things like, which it's now mitigated with the advent of CET, which we'll talk about a little bit going forward with the shadow stack, when control flow guard was first implemented, one of the ways to get around that is by overriding a return address on the stack. And I was working with somebody through this. And it was hard for that person to understand because of the lack of understanding that, when you do a basic buffer overflow, what you're really doing, right, is you're smashing the stack. There's a return address there. You can corrupt it, and then that return address gets executed. Well, that's what you do in bypassing something like CFG, a more modern mitigation, right? But you don't use a stack overflow, really. You use precision to locate a return address and override it. So by not understanding those basic concepts, it's really going to hinder you going forward. And when I say basic concepts, I don't necessarily mean, speed run your way through all these basic topics. Even if I would say it's better to do something once and fully understand it than, do a bunch of stack overflow exercises and you're just in the habit of like, you have a workflow on your notes or whatever, you know the commands to execute, whatnot. But really understanding those is kind of the segue into more modern exploitation. And that just came up in a Discord server. And by going back to the basics, almost sometimes it helps you with the more modern or contemporary exploitation, I would say, in my opinion.
Yeah, for sure. That definitely hits close to home. And with the whole overwriting the instruction pointer, it's like, no, you're not. You're overwriting a return pointer, a function pointer that you're redirecting the flow of execution, but you can't overwrite a processor register. Yeah, it's the same thing where like I find a lot of people, or run into a lot of people who have avoided programming their whole career. And so they're much more comfortable looking at assembly when they're doing reverse engineering than looking at decompiled code. But if you look at not that you shouldn't look at assembly, because sometimes decompiled code is incorrect, but what would be a couple lines of code decompiled, sometimes it's like 20 lines in assembly. And so the time it takes to read through that is greater than if you knew how to read the pseudocode well. So I think understanding the programming concepts and fundamentals in general, as well as the internals, using things like going out to, if you want to learn the kernel structures and such, the Virgilius project, and trying to understand all that, like all that stuff is key. So what do you think, I guess, what are the biggest pain points today in the kernel with regard to getting code execution?
Yeah, I would definitely say HVCI in terms of, if we think of like traditional unsigned code execution, right? So a lot of people may be familiar with a learning utility called hack sys extreme vulnerable driver. And when people do that for the first time, it's usually on a Windows 7 box, x86, and they allocate some shellcode in user mode, overwrite some kind of function pointer in the kernel, and redirect execution into user mode. And there's no execute bits, any of that stuff. And usually they do token stealing there. Well, things like that just simply are not possible. And I don't mean like, oh, you need to have some level of expertise in order to get there. I mean physically impossible on the machine. And I don't use that word lightly. Because all of those bits that are used to control execution permissions are managed by the hypervisor. And in order to make memory executable in the Windows kernel now, you need some kind of hypervisor vulnerability. Now, don't get me wrong, there are other techniques that you can do that kind of mimic shellcode, which we'll talk about later, but pure unsigned shellcode execution with HVCI without an additional vulnerability just in and of itself, it's not going to happen. And I think that has really shifted a lot of things because HVCI is code execution specific, but there are a lot of other things that are protected by the same infrastructure provided by HVCI. One thing that attackers like to do a lot is with VBS enabled, but HVCI not enabled, is there's a global variable called CI options that kind of manages the masks for, can we load unsigned drivers? Can we do X, Y, Z? And attackers, would patch that variable to say, yeah, open the floodgates, be able to load any unsigned driver you want. Variables like that are now protected by the same infrastructure used for HVCI. So it goes beyond code execution even, and taking a look at some of these other variables that we want to protect. We have things like the secure pool now that you can allocate objects in that are read-only essentially and protected by the hypervisor components. So I think just the VBS in general, but more pointed HVCI, I would say.
Yeah, for sure. So HVCI, if you had to give like a 1 or 2 sentence definition of it, what would you say?
Yep, I would just say the name, hypervisor protected code integrity. And essentially, as the name infers, code is now managed. I don't want to say managed, but the integrity of it is managed through the hypervisor. And so we have things like page table entries that describe memory. So this says, hey, this chunk of memory is readable. This chunk of memory is writable. What HVCI does is it enforces the concept of write XOR execute, or W XOR X. It says memory can either be writable or executable, but never both. And if you think about executing shellcode, for instance, what do we do with basic Stack Overflows? We write some shellcode to the stack, and then we jump to it. Well, the stack is executable before dep, right? When dep is enabled, what do? We use something like ROP to mark the stack explicitly as executable because memory is not executable by default with dep. We have boundaries between code and data. HVCI, to just sum it all up, you can't do that anymore. You need a legitimate entity like the hypervisor to do that on your behalf. You can't explicitly mark something.
Yeah, absolutely. So I guess with the technique, so let's say, for example, when SMAP and SMAP came out, like, for example, SMAP had a flag that was stored in one of the control registers, and if you could flip that flag, then you could bypass it.
Yep.
With HVCI, I know you're going to talk a bit about the bypass techniques. Do you see it being something where, like, a lot of these mitigations, once they figure them out well, you can't do it anymore? So, like, once they put that stake in the heart of this technique, being able to bypass HVCI might be impossible, correct?
Yes, exactly. And there's an interesting paper on the exploit database by, I think his name is Spencer Pratt, from a long time ago. It's using write process memory to bypass dep. And in it, he talks about, we're just going to play by dep's rules in this instance. And I think that's, sorry, I've got a dog sparking. When we think about HVCI, I think it's going to be more something like that, where we're not necessarily disabling HVCI or, explicitly doing what it's set out to mitigate. We're just going to be kind of living with it, if that makes sense.
Yeah, a bit like return to libc, where you're going and executing code that's already marked as executable.
Exactly.
Cool. Well, yeah, VBS in general is a scary thing. And, I always say this on the streams, like 20 years ago, I remember people talking about how you're not going to be able to do return pointer overwrites and smash the stack for much longer. It's going to be dead soon. And here we are, 2022. Most systems don't have shadow stack turned on or control flow enforcement turned on because the processors don't support it. And like with exploit guard, it's disabled by default right now. At some point that'll be turned on, so we still have some time. But like once that stuff starts coming on, I've been telling people, like, it's going to be a lot of one-off exploits. And the reason why that specific vulnerability is exploitable has to do with the conditions that just present themselves in a certain way. And it's the day of like teaching a technique that always works is probably, coming to an end here.
Yeah, exactly. I agree with that. And there's a paper that Matt Miller did when implementing arbitrary code guard, which is kind of, HVCI sometimes gets called the arbitrary code guard of kernel mode. And Matt Miller talks about looking at the landscape of exploits. And, when we think about the first exploit mitigations like dep, for instance, really good. It definitely changed the landscape, but it's almost like putting a Band-Aid on a bullet hole type of thing. Whereas these new mitigations, if you look at the blog that they released, they actually look at the root cause of what is actually when we get exploit primitives like read write, that's Microsoft's threat model, is all of their mitigations, they try to start with read write because that's what attackers going to have. Looking at what are the things that attackers are actually doing, and it's twofold. It's hijacking control flow, which we see the advent of these mitigations with control flow guard, CET, all of these extended control flow guard, for instance, even, or executing unsigned code. And we see the mitigation of this with like arbitrary code guard or code integrity guard or HVCI. So the mitigations today do a lot better job, not necessarily in the novelty of them, although they are more novel in many senses. It's actually addressing the root cause of the issue. And I think that's where we're going to see more of living with within the constraints of a certain mitigation.
Yeah, it's interesting. I did a talk a few weeks ago on browser exploitation, and it was like in 2014, I always talk about how Corland Coder and I called each other at the same time. So we're like, oh no, these exploits die, or they're not working. And it's because they threw out isolated heap and memgc around the same time. And isolated heap is pretty easy to get around, but memgc, it's still treating the symptoms and not the root cause, but it really did a great job. I mean, by making it so you verify all the other objects in memory that they don't have a reference to the object being freed, that really killed it for the most part. But that was still treating the symptom, when the root cause is the way that they chose to implement smart pointers in relation to the browser. But yeah, you're absolutely right. Going after those root causes, we got a lot of smart people there. I mean, Matt Miller's been heading up the MSRC and such for a while now, or at least in the mitigation space. Yeah. So let's move on then. Let's get to some fun stuff. Why don't you show us something cool and let us know what you're going to start off with?
Yep, I've got a few demos here today. First, we're going to start off with kind of your basic kernel exploit. So all of these are going to be on Windows 10, and then the last one will be on Windows 11. But essentially what we're going to do is we're going to take a look at what exploitation looks like with some of these VBS features turned off, the quote-unquote archaic primitives, if that's what the term you want to use. And then we'll kind of, each one will build off the last and kind of look at some interesting techniques. So I have Visual Studio here with kind of the code for all of this. I'm zoomed in pretty well, so hopefully that everyone can see this, but I'm monitoring the chat if somebody is having issues. And what we're doing is, for all of these exploits that we're doing, we are targeting a third-party driver. In 2021, I blogged about a Dell driver that had a write-ware vulnerability. So kind of, if you don't have experience with that, we're coming in with this exploit with the premise of we can read up any pointer we want in memory, or we can write any pointer we want to in memory in the kernel from user mode. So that's kind of the premise of what we're doing here. And the way that we go about this is there's a technique called essentially corrupting page table entries. And what exploits do essentially is, for the kernel mode, we want to execute some kind of shellcode. So this is synonymous across like your first stack-based buffer overflow or even a kernel exploit. We have some kind of raw assembly instructions, we want to execute them. But on modern Windows operating systems, there's dep. And what dep says, it says, hey, memory, we're going to separate it now. So if you have a data segment of memory, like code, or excuse me, like the stack, or the legitimate .data section, for instance, that never needs to be executed. It just holds data. So it's readable and writable. However, the text section, which contains your code, it is going to be readable and executable. We don't really need to write to it because once we compile code, it's all there for us. We shouldn't have any real dynamic code. I have seen a lot of bad software that does that. So there are still things that don't have dep enabled on them, I guess you could say, for x86. But the way that this works is we have this main function, and this is the shellcode that we're going to be executing. So I'm not going to spend too much time on this because there's a lot of documentation online about this. But what this shellcode does is, on Windows systems, there is a system process, and that system process is responsible for executing most kernel mode threads for the most part. So since it's executing kernel mode threads, it runs with kernel privileges. So it runs a system. It has a static PID, or process identifier, of 4. So what this shellcode does essentially is, by locating the current process, which is the process that's starting this exploitation, each process object on Windows in the executive has a active process links member. And that's a doubly linked list that points to all of the other process objects. So what we do is when we get a shellcode execution, we locate our own process, we locate the member of that object of our process structure for active process links, and we walk it until we say, hey, where's the system PID at? Once we find it by process ID of 4, then what we do is we steal the token. And again, each process has a token. This is a pretty well-known term in InfoSec, even outside of assembly, like when you think of web apps, etc. It's kind of just a way to perform basic authorization on your behalf. So this token kind of enforces the permissions of this process. So that's another member of the process object, and we apply it to our process. So we copy it over to our process, and then we're done essentially. And what that does is it elevates our process to that of system privileges.
Yeah, just a quick note there. I mentioned the Virgilius project. The offset to where the token is stored is very dependent on the build of Windows 10. So definitely check out that. You can see all the different kernel versions, and you can see exactly what the token offset is, so you can modify your shellcode.
Yes, exactly. So what we're going to do is we're going to look at the code just very briefly, but I have strategic breakpoints set up where we'll actually walk through in the debugger kind of the key steps of the exploit. So essentially what we do is, I'm not going to get into like the internals of, opening handles to device drivers, for instance. There's a lot of information online about that. I'm just going to talk about the more exploitation specific stuff, right? So Windows gives us this beautiful gift for medium integrity processes called enum device, or I think it's enum device drivers. I'm not entirely sure the name of the API offhand. I'm having a brain meltdown. And essentially what you can do is from a normally spawned process on Windows in medium integrity. So that's any default process, basically. For the most part, there are niche corner cases on Windows. If we come to this function, you can get all of the load addresses of the drivers, which are kernel mode addresses, from user mode, which is a wonderful gift that Windows has blessed us with. It's not a vulnerability. This is perfectly legitimate Windows functionality, right? So that's the first thing we do. We can locate the base address of the kernel itself from user mode without any vulnerability. And once we do that, we then write our shellcode to kernel mode. So as I mentioned beforehand, what exploits on Windows 7 x86 do is they allocate shellcode in user mode, and then they overwrite some function pointer in kernel mode. And when that function pointer executes in kernel mode, it redirects its execution up to the user mode. But each processor has a current privilege level, or CPL, and the code segment is set to 0, which means ring 0 or kernel mode. So even though we're touching user mode addresses, it's being executed in context of the kernel. Well, even with modern Windows operating systems that don't have VBS enabled after Windows 10 RS2, we have something called kernel control flow guard. And it's only implemented when VBS is, or excuse me, when HVCI, which we'll talk about later, is fully enabled. But there's a gotcha here. And the gotcha here is that even with HVCI disabled, which is what we have now, kernel control flow guard is a no-op of sorts, except for one thing. It performs a bitwise test on any function pointer that's being overwritten, and it verifies if it's a user mode address or not. So what this means is, even though we are redirecting execution into user mode, which is not what we will be doing here, and even though kernel control flow guard is not enabled, it still says, hey, I see you're trying to reach out to user mode address, crash, cause a blue screen of death. So instead, what we have to do, we have to write our shellcode to kernel mode instead. And we'll talk about some of the constraints there in a little bit. And where we're writing it is a structure called kuser shared data, which again, we'll see all this in the debugger. It's a static address, which it's not static anymore, but in Windows 10, it is static. And you can see right here, it's located at FFFF780 sign extended.
If you get a chance at times, can you zoom in a little bit? A couple of people are asking. I know it's kind of hard, but
yeah, no worries. Hopefully this is good to go right here.
That's very big.
Yeah. So then what we do is we are going to corrupt the page table entries, which again, this will be something that we see in the debugger. I'm not going to go into it now. And that's going to make our memory where we wrote it to, because again, we have dep in kernel mode. What does dep say? memory is either going to be writable or executable, but not both because of those boundaries that we set. But it can be violated, which is what we'll see in a little bit. And we violate it by kind of tricking the kernel or the CPU, excuse me, when executing our code to look at the page table entry and say, oh, this is executable page. Let me go ahead and execute the shellcode there. So I'll skip over this now because we'll see this in the debugger. Then what we do is we locate the how dispatch table. So how dispatch table is an array of function pointers that performs a lot of the functionality of the hardware abstraction layer, which again, I'm not going to get into right now. And the how dispatch table at an offset of 8 on x64, it's a function that can be triggered by a user mode function that we can call from user mode. And again, we'll see this in a second. So what we do is we corrupt that function pointer with the address where we just wrote our shellcode. So when how dispatch table plus 8 is executed, what will happen, it will execute our address instead of the legitimate address. It's called a function pointer overwrite. And then we call the function in user mode that I just spoke about, which is responsible for calling the function in the kernel. And when we do that, it will trigger our function pointer overwrite. And then we restore the old value. So I have this Windows 10 machine right here. And let me pull up the exploit and copy it over. Let's see if this will copy for me. Let me exit out of there and respawn the Hyper-V image.
And is a how dispatch table still overwritable reliably in Windows 10 and 11?
It is, but it is managed. It's looked at by PatchGuard. So yes and no. It is in the sense that PatchGuard, it's very hard to determine, when it's going to actually trigger and whatnot. But it is something that can still be overwritten, especially when you restore it. But that is one of the older or oldest probably generic function pointer overwrite techniques, I guess you could say,
yep.
On Windows, especially on x86. So I'm going to go ahead and execute this exploit. So I have this breakpoint set up here. And if you're ever doing kernel exploitation, a great utility to use is the debug break function. And what that does is whenever debug break hits, which is callable from Visual Studio, let me see an instance here, debug break, it causes the debugger, the kernel debugger that I have attached, to break in, and it's already in context of the process that triggered the debug break, which is very useful. So right now I have a kernel debugger over here. So when I press enter, it'll cause us to break into the debugger. And as I mentioned, let me make this a little bit bigger. As I mentioned, there's a structure on Windows called k-user shared data. And it's got all this interesting information, such as like system time, etc. And as the name infers, it's shared data. And historically, this has always been located at a fixed address. Even with address space layout randomization, it's still a fixed address, right? And that address is FFFF780000. So that's where our shellcode is written at an offset of 800, because when you allocate something with virtual alloc, for instance, it's always page aligned. So even if there's unused data at the end of the section, it will still be allocated memory, and it's all zeros at an offset of 800 into that address. So this is a shellcode that we talked about earlier. We used our write primitive to write all that shellcode to kernel mode. I'm doing PTE 0 because there's an error in PTE, the command. Sometimes it'll say levels not implemented for this platform. And a mentor taught me that you can do PTE 0 to get rid of that error. So that's why I've done it here. So what PTE does, if I take this address and I use this extension, it gives us a page table entry that corresponds to that address. And you'll see here the virtual address, which is the one that we're dealing with. So these are all paging structures, which are well beyond the scope of this presentation. we're only focused on this last one here, which a PTE describes a page of memory. Page on Windows is 0x1000 or 4096 bytes by default. So what this PTE is saying, it has some bits here, and it's describing this memory page. And what it's saying, hey, this page is K, it's a kernel mode page. This page is W, it's writable, and this page is V, it's valid. So we were able to use our kernel mode write primitive to write to a kernel mode address, K. And how could we write to it? Well, the page is described as writable, as W. You'll notice what it doesn't say. It does not have an X or an E, which depending on the debugger is responsible for the executable bit. We'll get into that in a second. So our shell code is there. It's good to go. So coming back to the Hyper-V machine, we've got another breakpoint here, and it says PTE base, and it says press enter to verify the PTE base. Now, what is the PTE base? So the PTEs are on Windows, they're stored in an array, in a virtual address, in a linear address for ease of access. They're really physical, but they also get put into an array of linear addresses. And historically, this was fixed. Like K-user shared data, the address was fixed in memory. On modern Windows operating systems, it's not fixed in memory. Why do we care about the PTE base? Well, in our exploit, what we're going to do, we're going to try eventually to corrupt the metadata of this PTE. And we're going to try to corrupt one of the bits here to trick the CPU into thinking this is an executable page and executing our code. Well, in order to corrupt this, what does that infer? We need to locate where this page table entry is. It's stored in an array, but now the base of the array, which is the PTE base, is randomized. So there's a function on Windows called mitigetPTEaddress. If you look at it, this function, as it infers, gets the PTE address associated with a virtual address. Well, what do we need in order to get the PTE? We need to index the array, and the array is randomized. So this function actually gets filled at runtime with the base of the page table entries because kernel mode callers need to use this to update memory permissions or do other things, etc. Right? So at an offset of 13, actually, if we use the DPS command, mitigetPTEaddress plus 0x13 and display one address, we see we have the base of the page table entries here. So with an exploit these days, what you have to do is you need a read primitive. And with the read primitive, you bypass kernel address space layout randomization first, which we've already done because Windows grants medium integrity processes the load addresses of all the loaded modules in kernel mode. Well, the kernel is a loaded kernel module, and we just get that. Once you've done that, you locate where mitigetPTEaddress is at an offset of 13, and that'll give you the base of the page table entries. So if we come back to the Hyper-V image, I know this all seems kind of arduous right now, but when we get into the next one after this, I'm not going to have to explain all of this, right? And if we look here and we look in the debugger, they're the same address. So that's kind of verifying, all right, we've used our read primitive successfully. We've got the base of the page table entries. So if we come to our shellcode, or excuse me, our code back over here, we see calculate the page table entry of k-user shared data plus 0x800. Now this looks like gibberish. Like, what the heck are you doing here, Connor? Why are you bit shifting and bitwise and adding all this? What we're doing actually is we are just using the same instructions that mitigetPTEaddress does. mitigetPTEaddress, this may look random, but these are actually compiler optimizations to fetch the page table entry, to index that array. So what you actually do is there's something called a virtual page number. And a virtual page number is kind of like a page frame number, which kind of describes the physical frame that backs the actual memory. And we can see this here, PFN. So if you took a PFN and you multiplied it by the size of a page, which is, let's actually go ahead and do that, because why not? If we take this, This is the page frame number. We multiply by the size of the page. That gives us the physical page, the physical memory address that backs the virtual page itself. And these have the, this is the K user shared data. So if we come here and actually unassemble this that we're looking at, or the K user shared data structure, excuse me, this is it in memory right here in the physical memory address, not the virtual, which is what we're dealing with. There is also that same concept for virtual addresses, virtual page number. So to index that array, what you do is you get the virtual page number, you multiply it by the size, or you divide it by the size of a page to get that, and then you add to the base of that page table entries. And what we do here is we kind of just do the compiler optimization. So we just say, hey, what is migetpt address doing? It's doing bitwise shift 9. It's doing bitwise AND with this value, and it's adding the base of the page table entries. We don't need to muck around with, actually indexing the array. We'll just directly mimic what that function itself was doing. So coming back to the Hyper-V image, come to connect over here. Sometimes you have to close this out.
Hey, Connor, quick question that I was talking about with somebody with the whole token stealing shellcode, which can obviously potentially be detected using read-write primitives instead to go and access that. Is that a technique you typically use, or is there any reason to do the shellcode technique anymore?
Yeah, so there is it's perfectly valid to use the token stealing. The reason why I don't do the token stealing a lot is because a lot of actual rootkits themselves or nation state level exploits, that's kind of just a POC that people do to elevate their process. So yes, you can do things like dump LSAS, etc. But really, if you're trying to do and I know this is going to sound pretentious and elite, I guess people will say, but if you're trying to mimic that level of functionality, you want API calls. You want to be able to call kernel mode APIs, and shellcode makes an extremely extensible way to do that. So if we think about like C2 frameworks, for instance, you got a shellcode blob. What is that blob actually doing? Just calling a bunch of Windows APIs that you're abusing for malicious purposes. So that's kind of the same concept I apply. You could bypass this whole entire talk and just do that all day long. Definitely, it's still valid 100%. So we got the PTE base now, so I'm going to press enter and come back to the debugger and press G. So we actually just looked at the page table entry that correspond to that. We got ahead of ourselves, so we verified that already. So we can go ahead and skip that. We saw how to locate the page table entry that corresponds to the shellcode address. And now I'm getting a bunch of stuff. I think I just executed the whole exploit, probably, didn't I? Yes. All right, we're going to go in reverse order of this. So if we come back to the page table entry, let me do 0 first. It actually corrupted the page table entry to mark it as executable. Then what we did was we overwrote, which how dispatch table. It'll be restored to its previous value, but let me go ahead and show what happened. So there's this function here called Hally query system information. What we did essentially is we overwrote this pointer with the address of our shellcode, which is this address right here. So anytime how dispatch table 8 is called, this address gets called instead. Well, the beautiful thing is we corrupted the page table entry to mark that page as executable. So once we overwrite this function pointer, when it's executed, we have executable code there, and it executes our shellcode, which steals that system token, applies it to our process. And if we come back to the machine here, we have system privileges now. Because our shellcode executed, it applied the system processes token to our process object, and that granted us system privileges. So that's kind of exploitation, what it looks like on Windows 10 machines without some of these advanced mitigations enabled. And we'll kind of build off this in the next one. And then we'll have one more demo before we enable the mitigations themselves, HVCI. But that's what we do now. dep says memory is not executable by default and anything that's writable. So think about, if you're familiar with return-oriented programming, use an API like virtual protect to mark the stack as executable. That's what we're doing here. We're just marking our region of memory as executable, but we don't need an API to do it. We can just corrupt the actual page metadata and mark it and say, hey, this is executable now. And there we're good to go. And kind of all of this is outlined on the screen. Cleared the NX bit. Then we corrupted how dispatch table 8. We overrode it, executed our shellcode, spawned a CMD, and now we're system. I'll look in the questions and see if there's anything here.
Just the one at the very bottom. Yeah.
Yep. How to identify if a kernel driver is enabled by SMAP or SMEP? SMAP and SMEP are OS level mitigation. So it's not something that a kernel driver would compile into or opt into. So I'm not sure if that's the answer. But to answer your question of how to know when those are enabled, there's a control register called CR4. The 20th bit is for SMEP, and I forget the one for SMAP, but it's documented in Intel. And you can look at those bits in the CR4 register to determine if the mitigations are enabled. For k-user shared data or how override, do you need to restore the original values? Wouldn't the system crash if you don't? Yes, indeed. It would crash, not immediately, but it would crash after a little bit. And it's twofold. It could be one, patch guard, or two, something legitimately is calling into that, and now we've corrupted it with garbage. Does patch guard check k-user or HAL on Win 10.11? Not sure about k-user, but HAL dispatch table is checked. But patch guard is so finicky, it runs on random timers almost. So it's hard to know when it goes off by default. That's why there's so few patch guard bypasses. And I mean true patch guard bypass to understand how the thing is implemented and directly attack the infrastructure of it, because it's so random and convoluted of how it's implemented. There's no symbol called KE enable patch guard in the kernel. There's nothing like that.
Yeah, the functions typically overwritten in the HAL dispatch table are very low demand functions. They're hardly ever utilized. I remember the original paper that was released on that said the HAL dispatch table offset +4 is never called after a week of the system up.
Yeah. Do you add a patch guard bypass to your exploits? No, not really. Number one, patch guard for our purposes we're not dealing with, because when you turn kernel debugging on, actually that disables patch guard as far as I know. And number two, restoring it is going to beat the timer. I mean, you're always going to have a race, technically speaking, with patch guard. So that is vulnerability number one. So we had a kernel driver for Dell that was loaded in the kernel mode. It had a vulnerability that we could read and write anywhere into kernel mode. We used those to execute some shellcode. Right. Now we're going to open up another POC to do this exact same thing, but with a different, more novel technique, I would call, and it's going to set us up for the rest of our stream. And that's corrupting something called previous mode and the thread object. So I'll do all of that again because we've seen how it works now. This is the exact same exploit, but the way that we do the read-write primitive is different. So same shellcode, same exact place that we're going to write it, same exact everything. Everything is the exact same. But we do something different now. And what we do is I have this function here called leak kthread. Leak kthread. This function leverages NT-query system information to leak the kthread object associated with a given thread. What does that mean? NT-query system information is another one of these absolutely beautiful functions that Microsoft gives us. It is a function that is callable by medium integrity processes, again, and it can leak. Leak is a strong word. It can bubble up back up to user mode the kernel address of almost anything you'd like. Threads, even if they're user mode threads, are still managed by the kernel. And they're managed by a structure in the kernel. You have your executive version, the E thread, and then you have your kernel representation, the K thread. The K thread is what we're going to be taking a look at. Calling NT-query system information from a medium integrity process, where we can see right here, NT-query system information. We can get all of the handles of the kernel of all the threads, essentially. Or we can get all the handles in kernel mode. We can walk them. We then look to see, is the current object a thread? That's denoted by the 0x8. If it's a thread, we see, are we dealing with a thread handle from our current process? Then we say, is this our target thread handle? So what this function does, this leak k thread, is we create a thread in user mode. Or we can open up a handle to our own thread that's executing all of this code for our exploit. We pass that handle to this wrapper that calls NT-query system information and bubbles back up to user mode the kernel mode address of the object backing that thread, which is absolutely amazing. I can't get enough of this, that this is legitimate functionality. So that's what we do. We can get the kthread object associated with our own thread. And the thread that our thread is the thread that's executing all of this code we see on the screen here. So that's what we do. Then what we do is we read in a member of kthread called previous mode. What is previous mode? Previous mode, if you're familiar with system calls on Linux, for instance, that same concept exists in Windows. It's just more abstract. So what I mean by that, on Linux, everyone's probably familiar. You have a system call number, you load that into whatever register, you do syscall, it does the operation. That exact same thing exists on Windows, but not directly. So you call a function like virtual alloc. It's actually just a wrapper that calls another wrapper, that calls another wrapper, et cetera, until you hit the NTDLL layer, the native layer. NTDLL, actually, I don't know why I'm preaching about this. Actually, I'm not going to show it in there. NTDLL, the version is called NT-allocate virtual memory. So virtual alloc eventually calls NTDLL, NT-allocate virtual memory. That loads a syscall and does a syscall instruction. What does syscall instruction do? Redirects execution for our intents and purposes to the kernel to start dispatching some, memory or some kernel managed object or utility. What previous mode is used for is when the call hits the kernel, because again, Microsoft has a hard conundrum here in general with the design, right? When you do a syscall, you're copying parameters from user mode into the kernel and you're parsing them and trying to use them in kernel calls, right? There's a lot of checks that have to be done to ensure, someone doesn't arbitrarily just put 41, 41, 41 and that gets copied and used in some call. Previous mode is one of those things that are used in checks. So previous mode is used when a system call happens to determine where did the system call originate from? Did it originate from user mode or kernel mode? If it originated from user mode, that's all untrusted input, and we got to do a lot of security checks. If it's not user mode, we infer, oh, this is a system call that's coming from the kernel, and we do less checks on those, right? So what we do is we corrupt the previous mode member of our kthread object, which we could leak because we use that function exported by Windows, NT-query system information, and we corrupt that to 0. Now, anytime we do a system call, the kernel is going to say, oh, your previous mode is set to 0. 0 denotes kernel mode. So anytime we call NT-write virtual memory or NT-read virtual memory, the kernel says, oh, this is stemming, this call is coming from kernel mode. And we bypass a bunch of checks, which we'll see here in a little bit. And then we do all the exact same exploitation. But we don't use the kernel mode read-write primitive from our first exploit. We just use the exported functions write virtual memory and read virtual memory. Why can we do that? Because we corrupted previous mode on our thread executing all this code, the kernel sees, oh, this is a kernel mode call to write virtual memory. Well, we can just write arbitrarily to kernel mode memory now. And we'll see that in some of the checks that are performed here. So let me build solution, and we'll run this again. This should not take us nearly as long, but it's the same exploit, but with a different twist to it. And again, this is needed going forward. Let's see, desktop exploit. Okay, so our current thread object is this address. So let me copy that down into Notepad, which you can't see off screen. We press enter. So let's get rid of all this. Here we go. So this is one of the most powerful commands in WinDebug, DX. You may be familiar with DT, many people. That's kind of the legacy of viewing types. This gives us so much more information here. And the way you do it is you have an address, for instance, and you add this star. This is like C syntax to dereference this pointer. You can't just do it directly for some reason. You have to kind of add the syntax where we say we want to view this K thread pointer and then dereference it. This gives us all the members of this kthread object, which is our thread executing our exploit code. So we come here, we add parentheses, and we want to view the previous mode member. Right now that's set to 1. So anytime we do a system call like write virtual memory or read virtual memory, that's got to be serviced by the kernel. The kernel says, oh, your previous mode's 1, you're a user mode caller, we're going to do a bunch of security checks on you. So we know how to view that information now. So we come back over here, and it says press enter to view previous mode again. We've corrupted it now. So we press enter, that's going to execute the debug break. We come back here, clear all this garbage. Exact same command. Our thread object, what is our previous mode? It's 0 now. Using our kernel mode vulnerability, we corrupted previous mode to 0. Okay. Come back to our virtual machine. Press enter to trace write virtual memory. So now what we're going to do is, instead of using the driver vulnerability to write our shell code to memory, we're just going to call ntWrite virtual memory, which is a exporter function on Windows. So everyone's probably familiar with shellcode injection or similar write process memory. That eventually makes a syscall that eventually calls ntWrite virtual memory in ntDLL. That bubbles down into the kernel to ntWrite virtual memory. So what we're going to do is we're going to get our current process using the process. No bueno. Okay. This is our current process's eProcess object. What we're going to do is we're going to set a hardware breakpoint, and that's going to say break on access if 1 byte of whatever we're going to put is executed. But we can also give the /p here. And everything a lot of the time is probably going to be calling write virtual memory, for instance, in the background, right? And as I mentioned earlier, what is the system process responsible for? Executing most kernel mode threads. So ntWrite virtual memory is probably going to get called a lot in the background, but we want to view the call that stems from our process. And we can denote that in WinDebug. We'd say /p, the process object, that says break on access if any byte is executed within the process, our process object, for ntWrite virtual memory. Come back to here. Press enter. And we hit the write. If we look at the call stack, I'm not going to load my symbols right now because it's going to display the source on the screen and it's going to be nasty. This is our process, exploit.exe. What does it do? It calls ntDLL, ntWrite virtual memory. What does that do? Makes a system call that goes to the kernel and calls ntWrite virtual memory. Now I want us to look at something here. Okay. This is a wrapper to this mi-read virtual memory. So using the T, which is step into, we're going to go into the wrapper. Okay. Now I want everyone to look at this. The GS segment register. So segmentation is a pretty well documented old concept, and there are special registers that have constants in them essentially. And the GS segment register at an offset of 188 points to the current thread on this processor servicing this. Oh God, let me move this over to the other screen. Okay. So what this does, this assembly, when we reach this function, it's going to fetch the current thread that's responsible for executing this system call. Then you'll see something here. At an offset of 232, it grabs a value. Well, if we do dt_nt kthread, we do previous mode. Where's previous mode located at? It's located at 232. So this is going to extract the previous mode for the system call, the thread responsible for executing this. Okay. And then what happens? A test happens. So let's speed up execution to reach where that's happening. So the current thread is an R14. We do the thread extension on register 14. This thread comes from exploit.exe. That's us right there. We extract previous mode. Previous mode is an EAX. AL is the lower 16 bits of EAX. What did we do with our previous mode earlier? We corrupted it, so it's 0. This does a test. The 0 flag, it's set, and we're going to jump equal. What this is going to do, it's going to jump to this address. Now, I want everyone to look what would happen if this jump did not happen. So if previous mode was 1, we compare RDX, which is the memory address we want to write to, with 7FFFFF0. That's technically speaking on a 64-bit system that's not LA57 processor, where technically only 48 bits are addressable. That's the highest user mode address you could write to. And that gets compared. And a jump would happen if it's greater than, so jump above that value. So if we're writing to a kernel mode address, for instance. And if we look at this memory address, that puts an NT status value of C005, which I think you can get that error with the win_debug command. The instruction reference memory, the memory could not be. That's basically, for all intents and purposes, no, you can't write there. So if previous mode is 1, we cannot write anywhere greater than this address, which makes sense, right? We're user mode caller. We should only be able to write to user mode memory. But we're a kernel mode caller now. We're not a user mode caller. And we make the jump. And now there's no checks now. We can write anywhere in memory using normal system calls. So we don't have to use the kernel vulnerability anymore. We just use system calls to NT write virtual memory, NT read virtual memory. Come back to our debugger, or excuse me, our machine. And I'm not going to step through everything else because we've already seen it before. Instead of using read64 and write64, which were the wrappers for the functions we were seeing earlier, we now use the system calls. And if we look at who am I, we're NT system. So we did the exact same thing as last time, but the read-write primitives we did were from the read and write primitives were from system calls instead of the actual kernel vulnerability. I don't know if I cut out there. I saw you go away for a second.
No, that was just me. Don't worry about it.
Okay, yeah, no worries. So I know that sounds pedantic almost to do that same thing over again using that, but that is what we're going to use for some of the techniques that we use using HVCI. Okay, so I'm going to look at the questions here. Is any of this code available to us? Yeah, I can publish it afterwards on GitHub. What gadgets do you use to perform the previous mode override? We don't use any gadgets, actually. So if we come back to our exploit, we use the kernel mode vulnerability. Once we grab the previous mode using read64, which is using our kernel exploit, which again, I've blogged about that. We're not talking about the actual vulnerability itself. We just know, hey, we have a kernel exploit that can do read-write. And we just manually set using write64, which is a wrapper, for an ioctl send to kernel mode to do the write primitive, which again, you can go look at that blog to actually see how the vulnerability itself works. So we kind of did the same thing, but now we know we can kind of corrupt that previous mode and bypass a lot of checks, which is a very interesting way to go about it.
A lot of questions often come up around just getting into driver debugging and exploitation. And my recommendation always is to go and just write a driver, like go look at a tutorial on writing a driver using Visual Studio Code or whatever. And that's going to teach you a lot about the IOCTLs and IRPs and how the whole thing works.
Yes, exactly. I recommend that to lots of people. The thing is with exploitation, browser is something I was really afraid to get into for a while. And I lied to myself, basically. I lied to myself. I said, if I read some of these Project Zero blogs and whatnot, I just won't do browser exploitation, but I'll understand it. I'll just go ahead and read and kind of supplement there. It wasn't until I actually did it that I realized, wow, that there's a lot that I'm missing here. So reading documentation is great, but actually doing it, as you mentioned, there's nothing better. Okay, so that is that. Let's go to kCFG. Just so everyone can see, I got a bunch of POCs here that I'm going through. Okay. All right. So this is going to be the last kind of prereq bug that we're going to do. Okay. So what has our exploitation relied on so far? It's relied on, if you come back here, I cleared the screen already, of course, overriding a function pointer. There's two things we need for exploits to succeed, as Matt Miller says, especially in our case. Hijacking control flow, so being able to control the instruction pointer, and executing unsigned code, getting executable code. Executable code, that's not an issue right now. We can corrupt page table entries. But what has our exploitation relied on so far? Corrupting how dispatch table plus 8. That's checked by control flow guard. Right? So now let's kind of, control flow guard isn't fully enabled until HVCI is turned on. But for our intents and purposes, let's pretend that kernel control flow guard is enabled right now. So we cannot do a function pointer override. And I'll explain kernel control flow guard. I'll just explain it right now. So control flow guard, if you're not familiar, oh, let me see this. I think he used ntquery to locate the kernel address for his current process's kthread, yes. And then use a write primitive to overwrite previous mode. No ROP gadgets are finding kthread. Yes, that's exactly how that went, just leaking kthread. So control flow guard. What we've been doing so far is we're overriding a function pointer. Well, Microsoft saw this in a lot of browser exploits because browser exploits, and I'm sure Steve can attest to this, in the prime in 2013, browsers are written in C++. They got all these wonderful virtual function tables. Well, there's a lot of use after free issues with those objects that call methods on those tables, right? So you could basically kind of fake your own virtual function table and overwrite a virtual method that would have been called otherwise with your own shellcode or ROP chain, for instance. So function pointer overwrites in the prime are happening all the time. Well, Microsoft saw this. And in Windows 8.1, as an optional update, they shipped something called Control Flow Guard. What Control Flow Guard does is at compile time, we create a dictionary, is what I'll call it now. It's actually a bitmap, but we'll call it a dictionary. And what it does, it says, hey, anytime I'm doing an indirect function call, well, what's an indirect function call? It's a call to something that's a non-absolute memory address. So if you think of call RAX, call through register, that's an indirect call, because how do we know what's an RAX when that call happens? It's indirect. Or call through a pointer, call pointer X. Well, what's on the other side of that pointer? We don't know. Those are indirect calls. Anything that is used as a call target in an indirect call gets shoved in that dictionary, a bitmap. And anytime an indirect call happens now, we look at that bitmap and we say, hey, whatever's on the other side of that function, do we know about it? Is it in this dictionary that we know about that are legitimate call targets? If it is, great, we're good to go. Call. If it's not, we crash. Well, what did we overwrite HAL dispatch table with? 0xFF, FFFF7800, K user shared data. That's not a function. That doesn't get called. That's just memory. So when you overwrite that function pointer, the check happens. We look in the bitmap and we say, hey, I don't see K user shared data here. Crash the process. So for our intents and purposes now, we can't overwrite function pointers. However, kernel control flow guard does what? It looks at indirect calls and jumps. That's not the only way to transfer control flow, right? When a call happens, what gets pushed onto the stack? Return address. when the caller is done executing, return execution back to the callee. Well, what is that used for? To know where to return execution back to. It transfers control flow. So a well-known limitation of kernel control flow guard is return addresses. And that's mitigated now, which we'll see in the last demo. But for now, we can overwrite return addresses on the stack. And as Steve and I were talking about earlier, this comes back to basic stack-based buffer overflows, knowing what you're doing with that. You're overriding a return address on the stack. We're going back to the basics now. We don't flood the stack. We don't have a stack overflow, but we have techniques to leak the stack, override it, use precision to find a return address, and be on our merry way. So we're going to do that all here in this exploit. So everything is the same here. We're writing to k-user shared data. We're corrupting the page table entry to mark it as executable, and we're going to hijack control flow. But instead of overriding HAL dispatch table plus 8 now, we're going to be overriding a return address on the stack. Let me view these before I get into it. Talking amongst themselves. Great. Okay. Let me get a drink of water because it's going to get spicy here in a little bit. Okay. So same shell code, right? But instead, we have these placeholders here. And I'm not going to talk about these right now because I'm going to talk about the rest of the exploit. But we have placeholders here that eventually need to call ZW terminate thread. Okay. Shell code's here. Everything's the same. Write the shell code. Resolve our needed functions. This is kind of the software dev and me doing this kind of assertion type stuff. We leak the K thread of everything's the same. We corrupt previous mode of our current thread, all that good stuff. But now we have this create dummy thread, right? So the stack, when we say the words the stack, there's kind of this misconception that the stack is this fixed place and there's one stack. Yes, that's true. There's a region of memory that's allocated for the stack. But really, there's a bunch of stacks that are allocated for each thread. So each thread gets a stack. Now, this takes a little bit of Windows internals knowledge. I'm not going to get into the kind of whys. It's actually self-explanatory when you think about it. Every thread has both a user mode stack and a kernel mode stack, even if it's a user mode thread. It's just not transparent to the end user, right? I call create thread. I have a user mode thread. Great. I can operate on it. I can do whatever I want with it. Under the hood, the way that threads, again, these are managed by the kernel. These are objects managed by the kernel. All the methods responsible for setting up the thread, all that good stuff, APCs, which we'll talk about a little bit, all that, need to use that space for the kernel calls in context of that thread. So all that's there. So what we can do is we could create a dummy thread. We don't care about this thread at all, okay? If we go to create thread in common.c create dummy thread, it calls create thread. And the entry point of this thread is dummy thread entry point. And if we view this, this literally just does return and void. It's nothing. We don't care about this. This is garbage. We don't care. We have a dummy thread because we want a thread that we don't care about. Sometimes it's good not to care. We don't care about this, and that's a good thing in this case. We update the payload, which I'll talk about in a little bit. Let's see, corrupting the page table entries. And we'll see this all in the debugger. This is a bit confusing now. Leak K thread of our dummy thread. So up until this point, we've leaked the K thread of our own thread that's responsible for executing all this code. Well, this is just a wrapper for any thread. So we can get the K thread that maps to our dummy thread. Well, what do threads have? Stacks, right? So we can leak the K thread of this dummy thread we don't care about. Then we can get the stack base and stack limit of that thread. So using NT read virtual memory, we can index that structure at those offsets to extract those members to get the thread for that, or to get the stack for that thread, a kernel mode stack for that thread. Well, what's on the stack? Return addresses that we can overwrite. I'll explain the target return address in a little bit, but what we do is we scan the stack then. So we look at the stack for all the return addresses until we hit the one that we want to overwrite. We overwrite it with our shell code. And then eventually resume thread will kick off execution and execute our shell code. Okay, but we'll see this all in Debugger. This one makes a lot. Some of the other ones, the code is more explanatory. This one will make a lot more sense in the Debugger. Any questions in here? The DB driver has blatant read-write vulns. I don't think you need ROP for that. Yes, you don't need ROP for that because of the read-write vulnerabilities. This is kind of just a outlining very quickly and easily for that sort of thing. But that's what most exploit writers today do. Like if you think of Stack Overflow, you don't really get a read-write primitive. You just kind of overwrite the stack with some content, right? In our case, in more modern exploits, you need to get that read-write primitive. Could you use your read primitive to read the kCFG bitmap to find an address that already trusts and overwrite that instead of using the dummy thread? Yes, you could, but as we will see going forward, when HVCI is enabled, the kCFG bitmap is protected and is read-only. Okay, so let's come back here. x64, debug, exploit. I like these questions in here, kind of getting ahead of ourselves. That's why we're kind of taking this progression, because that is exactly where one's mind would go. Well, why are we doing this? Let's just overwrite the bit that corresponds to it. Microsoft has also thought about these things. So that's exactly why we are going about it this way. I like it.
Yeah, I feel like they slowly take away the fun. They're not just going to take it all at once.
Yep.
It's a little game we like to play.
Exactly. And then they like to put it in the insider build, and then it's kind of like a ticking time bomb. Well, when is this going to make it into prod? Okay, so everything is the same. We get the kernel base address. We write our shell code to k-user shared data. We corrupt it, clear the NX bit. We're all good to go. Here's our dummy threads k-thread object. Okay, so I'm going to copy this down. Press enter to view the call stack of the dummy thread. Perfect. Gladly. Okay, copy this. Okay, so we don't care about all this stuff. This is our dummy thread, right? One thing that I didn't tell or say is we created this thread actually in a suspended state. That's a very important piece of this. So if we look at the call stack, we see these functions here. We see the thread started, thread startup, we see this APC interrupt, deliver APC, and then we see this wait for single object. What a thread that's suspended on Windows is it is actually a thread with an APC queued to it that tells the thread don't do anything, wait. And what that thread is looking at, it's actually looking at the suspend, or what that is looking at, it's looking at the suspend count of the thread. Right now, the suspend count is 1. The way you decrement suspend count to 0 is called resume thread. That's exactly what our thread is doing. It's looking at suspend count. It sees it's at 1, which because we've suspended this thread, and it's looking to say, hey, when this goes to 0, I'm executing, I'm going to execute my entry point and all that. But it's 1 right now because we created it in a suspended state. Well, how does that happen? An APC, I'm not going to get into the APC internals, but APC is a way to tack on some work to a thread. So threads execute code. APCs execute code too, but they execute code in context of a given thread. You can think of it like as a thread callback, for instance. That's exactly what happens here. APCs are actually executed through a type of software interrupt. And an interrupt basically is a priority level. So there's something called an IRQL, IRQL, interrupt request level. And that's exactly what an APC does. It raises the processor's IRQL to 1. So we have multi-processor systems now. Each of them have an associated IRQL. Raises it to 1. What that means is any interrupt that happens at less than 1 cannot preempt what's currently happening. So this is like for hardware, for instance, right? You've got a very critical task that you need to run. You raise the IRQL. That way you can execute whatever you need to execute without anything at a lower IRQL preempting you and causing you to not be able to execute that. I'm not going to, this is all things that is documented by Microsoft. I'm not going to get into it. But we need to know this because if we look at the stack, what do we see here? KI APC interrupt. An APC gets queued to this thread to tell this thread to do nothing. Well, how does an APC get queued? Through a software interrupt. Okay. So every time a suspended thread happens on Windows when you create it in a suspended state. This function, as of right now, this is subject to change, will be on the call stack because we need to queue an APC, which tells the thread don't do anything. So when we talked about earlier, we need to target a return address on the stack to overwrite. That's the return address we're going to choose. And that's because this should always be here. And I want to show the internals about this just 1 second because I'm kind of a geek about this. If we look at PS user thread startup, that was the function that was called right before this happened, right? So if we look at this, we see this right here. And the return address is the instruction after the currently executing instruction that goes onto the stack. So I'm going to have to just try every value here until I get a valid instruction because I'm not familiar with the disassembly offhand, but I know what I'm looking for. Okay. The instruction that was executing that caused the return address to get pushed onto the stack, which caused the call to APC interrupt, was what? Move R15 CR8. CR8 is a register on Windows that contains the URL for the processor. So R15 before this had a value of 1. 1 is APC level. So that says, hey, only anything greater than APC can cause an interrupt on this processor. That gets moved in the CR8 register. So that raises the URL to 1. Well, now we're operating at APC level for APCs. That allows the APC interrupt to happen and causes the APC to get queued. Exactly right here. That's exactly at a technical level where this happens, right? Another thing to notice, code, so user mode and kernel mode code runs at an URL of 0, but APCs run at 1. So that's what happens. The URL gets raised to 1, and then the APC interrupt can happen. So that's going to be there every time. So what we do in our exploit is we store the address of kAPC interrupt 2F0. Well, we can leak the thread of the kernel mode representation of our thread, which has the stack, and we can just use read, our read primitive, read the stack until we see that return address. When we see it, break. Then we call write virtual memory on that with the address of our shellcode. So come back here. Man, we're doing live demos in the kernel and not one blue screen of death yet. Knock on wood. Okay. So overwrote the target return address on the stack. Press enter to view the corrupted stack. Okay, we have the thread object. Press enter. Let's look at the thread call stack again. What do we see now? We see our call stack is at 8000. Well, what is this address? Our shellcode. So when this unwinds and this return address gets executed, or this return address gets loaded, it thinks that this is a return address for kAPC interrupt 2F0, but it's not. Well, how do we return into this? What does the APC do? It causes a thread to wait on the suspend count to see it go back to 0. So the way that unwinding happens is when suspend count goes down to 0. How do we get suspend count down to 0? Resume thread that decrements the count. So what we can do is we literally create thread in user mode, do all this corruption we talk about, then we call resume thread in user mode that kicks off the execution and will execute this return address, which is our shellcode, right? With one caveat. If you've ever done a basic Stack Overflow before and you do stack corruption and you execute your shellcode, what normally happens to the application? It's toast because there's no restoration happening. Well, why is that? The stack isn't just for exploitation. The stack contains legitimate information, parameters, return addresses that need to be used. Well, we've just completely mucked up the stack. We've just shoved absolute garbage on it. And that's what's going to happen here because we overwrote the return address with our intended data. So the stack is going to panic essentially and say, oh my goodness, I don't know where kAPC interrupt 2F0 is. We're going to blue screen to death because some code legitimately needs that return to happen. So what we do is we kind of do a hack of sorts. We call ZW terminate thread. This is where our shellcode got updated earlier. RTL copy memory. So what we did is we had these placeholders earlier. And in the placeholders, we copied our current thread, our dummy threads handle, and ZW terminate thread. And what that will do is, after our shellcode executes, ZW terminate thread will be called, and it will be called on our current threads, on our current thread. Well, this is a dummy thread. We don't care about it. We just want to do the ROP, or not the ROP, we will in the future. We just want to do the return address overwrite, and then we don't care about this thread anymore. It's not critical. ZW terminate thread tells the kernel, hey, handle this for us. Terminate the thread. And it gracefully terminates the thread and allows execution to continue. Because unlike user mode, after we get our shell, if the server-side application crashes, that's fine. Maybe if you're a real nation state, you don't want to go detected, so you don't want it to crash. We're going to blue screen to death if we get a crash in the kernel. So that's exactly what happens. Now we prepend a stub at the end that calls terminate thread, and it bitwise aligns the stack to 10. On 64-bit, it's documented fast call for Windows API calls. You need to have the stack 10 byte aligned, and that means it needs to end in a 0. Why is this? We have XMM registers, which can move 16 bytes or 0x10 bytes of data at a time. And if you don't align the stack, if an XMM register ever gets used and it uses that 0x10 bytes, it may be an invalid address because of that, because it's expecting an alignment. I've learned that the hard way, actually. We align it before we do the call. Okay, let me press enter here.
Yeah, that's those little tricks that save you a ton of time if you don't.
Yep, exactly. And that's what I mean about, when I talk about browser exploitation and reading it. Some of those things you literally just cannot know until the situation arises, unfortunately.
There's a good question on the stack from E, if you want to check that one out.
Yep. Does Windows have a kthread linked list eProcess equivalent? Could you hijack an existing thread instead of creating your own dummy thread? Kthread does not, because kthread is the kernel implementation. eThread has a list of threads. We can look in the debugger, I'm almost positive. And that's because E is the executive. That's like the object manager and all of that good stuff. So if we do like btnt eThread, if we do list, thread list entry. So there is similar for the threads. But the thing is that it may require a little more work, because then you have to get the E thread, then you have to parse this and then go back to the K thread. An easier way to do that, an existing thread, is just to not create a thread, just open a handle to an existing thread and do it that way. The reason why we use a suspended thread is because we always know that return address will be there. With an existing thread, the call stack may be different. You may have to look into stuff. Have you experimented with using other types of kernel mode payloads? Turn into buff, load a rootkit, spawn a process. Would you add kernel exploits into red teaming for post-exploitation? Being on red team before, a lot of people are scared of kernel, and rightly so. One thing, you've blue screen if you don't take everything into consideration. So that's one side. The other side is we'll see in our exploit for HVCI where we terminate a process. Sometimes things have to be done in kernel mode for more complex things. So for me personally, I don't think it's there yet, but I think red teaming could get there in the future. I'm sure there are mature red teams out there that do this type of rootkit stuff, but it's not in the mainstream for right now. It's more, what I see these used for is less on the rootkit side right now. At least what I tried to do when I was in red team is write like a kernel exploit, for instance, to give you that privilege escalation to do something like dump LSAS or whatever, and then you're on your merry way. But those are kind of far and few between. And yeah, that was our exploit there. Enjoy the system shell. So this was the exact same exploit as before, but now we overwrote a return address instead of overriding a function pointer. Okay, now we're going to get into the fun stuff. So if you've ever heard of HVCI before, which I will talk about while this is rebooting, it's under memory integrity. in exploit settings. So I'm going to turn this on. Require a restart. So let me do this. Trying to get a browser up really quickly. I'm just going to use my blog for a few diagrams, just because it's easier. Okay. So HVCI, all of our exploitation up until this point has required us corrupting the page table entries to create executable memory, essentially. Because k-user shared data is a code cave that is not executable by default. So we need to corrupt the page table entry to make it executable. Well, just like all good things, Microsoft knows about this technique. And now the page table entries are technically managed by the hypervisor Hyper-V, which is Microsoft's hypervisor. Okay. So this blog, I'm not going to go through everything. I'm just going to use a few practical images so that you can see. Okay. Okay. So with VBS turned on, VBS creates something called virtual trust levels. And virtual trust levels, for all intents and purposes, are virtual machines. And what I mean by that is they are not virtual machines at a technical level. They do not have virtual hard disks. They do not have virtual network adapters, any of that stuff. They use the same concepts that virtual machines employ. What do I mean by that? So we take a look here. Child partition. Let's consider this. Let's consider this child partition a virtual machine. And this is the physical computer, right? Virtual machines run inside of a physical computer, right? Each virtual machine has its own address space, physical address space, right? So the VM, it has what it thinks the 0x1000 is, but that it actually exists at 4000 on the underlying operating system, right? Because again, virtual machines run in a physical computer. So all of your memory that's in a virtual machine, your VM sees, like for instance, if we come here, right? We're debugging a virtual machine. We have this address. This is the load address of our kernel, right? Well, on my physical operating system, this address may not be mapped. It may be mapped to something we don't know, right? All of the memory for the virtual machine technically is backed by the physical computer itself, right? What happens is an abstraction layer is added into the fold where VMs think they are operating on memory as if they're the only OS running, right? So the VM boots up. It's running its own operating system internally, like let's say Windows. We go to access 0x1000. Well, 0x1000, that doesn't actually exist because it's in context of the VM. What happens is something called a guest physical page gets emitted. And the CPU intercepts that and it says, hey, VM, I see you're going to access 0x1000. That memory that you want is actually at 0x4000. Let me do some translation for you so you can get that information and you can be on your merry way. That's how virtual machines work. That's how their memory access is gated. It's gated by the CPU. That's why you can run your malware in a virtual machine and it's isolated. Because on the back end, when you go to access memory, the CPU is a higher entity, or the CPU intercepts that via the hypervisor and performs translation for you of where you need to go. It is responsible for making sure you don't just arbitrarily do things, right? And this is at the hardware level, right? Let's come here, not to here. We can do the exact same thing here. Abusing these same principles, when what is called as normal world, which is our traditional user and kernel mode, which is what we're operating in now, when we want to access memory, the same principle that the hypervisor uses to gate memory access can be used for virtualization-based security purposes. So what happens is when VTL0, which is the traditional user mode and kernel mode, goes to access the memory, let's say we go to execute some k-user shared data. That's actually gated now. And we can perform some interesting access checks. And again, this is not full-fledged. It's explaining, this is a 91-minute read blog. Like, I don't have enough time for everything. But at a very high level, that's what's happening. So here's where it gets interesting. All that translation we talked about earlier is used through an extended set of page tables. So page tables is kind of your translation to get to where you need to go in memory. So you have a virtual address, for instance. That virtual address needs to get converted to a physical address. There's a set of paging structures. You can think of them like a car wash with varying levels of cleanliness. So you go through your first car wash, it kind of, gets the bugs off. You go through your next car wash, it kind of gets the car clean. You go through your next one, it shines it. That's kind of how you can envision page table entries. They go through these 4 structures that eventually on the other side give you your full-fledged physical address. Well, if we look here, when VTL0 and VTL1 are enabled, they actually, the extended page tables map to the same physical memory. And what that means is we don't use the extended page tables for translation. In our VM example, we did, right? We need to know how 0x1000 maps to 4000. So what happens on the back end, there's a VMCS, that's a virtual machine control structure. It is associated with a VM. It contains a pointer to the extended page tables associated with that VM. When this VM goes to access 0x1000, we index the VMCS for that virtual machine, get the extended page table directory associated with them, and we go through the process. We don't do that anymore for the 2 VMs, VTL1 and VTL0. We have the extended page tables, but they're not used for translation. What they're actually used for is to create an immutable set of permissions, a different set of memory permissions. So if we come here to a practical example. Okay.
And is this using level 5 of the page table mappings, or is this just secondary level address translation separate from?
Yes, this is the term extended page table through Intel is actually just Intel's implementation of second layer address translation. SLAT, yeah. Exactly. So did I put it in here? Okay, I'll have to explain this then. So we were able to locate the page table entry that corresponds to our shellcode. What happens now is that page table entry, that's all, we can locate that in the kernel, right? That's all stored in the kernel. So that's all fine and dandy. But that is the page tables, our normal page tables. The extended page tables, which are associated with VTL0, are stored in the hypervisor. And VTL1, which is secure world, can request through a hypercall, which is essentially a system call to the hypervisor, that says, hey, configure these extended page table entries with these permissions. So what happens now? In our last example, oh, see, I'm getting an error. Okay, that's all fine and dandy. We actually could just do exactly qntmi get pt address. So let's take 0x1 2 3 4 5 6 7 8. Let's 0x100. Shift right by 9. Oh, did I put an extra 0 in there? Take this. And this. That does not look right. All right, well, my math is off right now. Oh, I didn't do POI. That's why. It's doing the literal address. I need to dereference that to get what it points to. Okay. Okay. So we kind of have to do things a little bit differently now. So here's the page table entry that corresponds to k user shared data plus 0x800. Okay, this no execute bit is set. What we did previously is clear it. Well, that's the kernel's page table entry that says this is not executable. But the hypervisor has the extended page tables that also has a mapping for k user shared data plus 0x800. And it says it's also no execute. So even in kernel mode, if we clear this no execute bit, we still didn't clear the hypervisor's execute bit. And what did we talk about earlier, that when VBS is enabled, we can gate memory access and check it. So that can get intercepted by the CPU, and we look at the hypervisor's page table entry, and we say, hey, that hypervisor entry says it's no executable, even though the kernel says it is executable. We're not going to let that execution happen, and we crash. So the TLDR on this is the hypervisor has the true page table entry permissions for memory, and that cannot be compromised by the kernel at all. So let me show you what happens. So we'll do a break on access on 0x 1, 2, 3, 4, 5, 6, 7, 8. I know I sound like a child. Plus 0x800. Okay. Anytime this gets, actually, no. No, let's do that. Let's do that. Okay. So we're going to run the exact same exploit again. Exact same thing, but we have HVCI turned on. Let me see what anyone is saying. Looks like more containers, C groups. Not sure what that means. Okay.
Yeah, thanks for explaining that about the hierarchy there, because I think that's really important to note about the permissions hierarchy.
Yes, definitely. I need to be on the desktop. Okay. So we're going through our exploit again. That does the debug break. Okay, all fine and dandy. Press enter. That's fine. We don't care about this anymore. Did I turn it HVCI on? Oh, there we go. Okay. So I try to execute this, the breakpoint. What happens when I try to execute? Access violation. Well, my good sir, it says that the no execute bit is 0. So this means this page should be executable, but no, it's not. Because, again, a check happens to look at the hypervisor's view of memory. And who configured that memory? VTL1 through a hypercall. VTL1 is secure world. And what they do, I'm speaking to them like they're a sentient entity. What VTL1 does is it configures write, XOR, execute. Memory can never be both writable and executable at the same time, and that's enforced by the hypervisor. So now if I do go not handled, blue screen. Nothing changed. That was perfectly valid executable memory. But again, that's the kernel's mapping of memory. That's not what the hypervisor says. If we look at analyze, oh, I got this weird error, don't I? It's not going to give me the call stack, is it? Yeah, I've been getting this weird error on this VM for a while. Anyways, I'm telling you right now that we can't execute this memory, and we just tried to, what we did is we didn't crash because this is a VBS bug check. What we crash is the same as like executable memory, right? Because we're trying to execute memory that is not executable. Okay. So how does this change things for us? Okay, I'm almost done with the demos. I know people are probably getting tired of hearing me talk. So this is the basic POC. Right. Was this the one? Perfect. So everything is the same. Every single thing is the same, except for one thing. Oh, my VM went over to the other side. Okay, there we go. Everything is the same. So we're doing the exact same thing, right? We get the stack. We corrupt the stack because we know that KIIPC interrupt is going to be there. We read the stack, and once we find it, so store the stack address, we call this construct ROP chain. Okay. ROP chain. This function creates our ROP chain. Perfect. It accepts two parameters. It's a wrapper. The target return address and a handle to the dummy thread. So we use, also another thing, we've proven the point now with NT-write virtual memory that we can do that with previous mode. I'm using the write primitive because I don't want to set up 100 calls to NT-write virtual memory. That is also the thing about exploit developers, path of least resistance. Anyways, so what we do now is we overwrite the return address with a ROP gadget. So TLDR on ROP. ROP is really not this mythical thing that we think about. Oh, you've got this ROP chain. It does all this stuff, blah, 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 blah. It's a very simple explanation, actually. What does return do? Return at a technical level loads the stack pointer to the instruction pointer. What can we not do? We cannot execute code we cannot execute anything that is not executable. ROP gadgets are code snippets from the .text section. The .text section contains code and it's executable. So we are reusing existing executable code is what we're doing here. And all of the code snippets end in a ret. Why is this? Ret loads stack pointer into the instruction pointer. So when this ROP gadget goes to get executed, it does pop RAX. Then what does it do? Return. What does return do? It goes to the stack, picks up whatever's on the stack, loads into the instruction pointer. A prerequisite for ROP is the stack control. Because your ROP gadget, when it does the ret, will go to the stack, pick up whatever's there, load it into the instruction pointer. Well, what should be there when the ret happens? The next ROP gadget loads into the instruction pointer, executes, does the ret. So by nature of how ret works and controlling the stack, ROP kind of does this back and forth, picks up the next gadget, next gadget, next gadget. So we cannot execute unsigned code. That's done. We can't do that anymore with HVCI. But we can execute existing code. And if we think about what shellcode does, shellcode, like if you think about a Cobalt Strike beacon, for instance, what does it do? It opens up some network connections, writes some files, opens some other processes using legitimate Windows functionality for the most part, calling through Windows APIs. So shellcode is just a very easy way to call Windows APIs. If we think about our last exploit, how did we call ZW terminate thread? In our shellcode, we just set up the arguments. We can't do that anymore in shellcode, but we can still use ROP to call into Windows APIs. So here's a proof of concept. Everything is the same, but we have a ROP chain now. And I'm going to set a breakpoint on this first ROP gadget. So when the return address is overwritten, it'll be overwritten with this address, which is pop RAX. And then we'll take a look at the stack and our ROP chain should be there. Hopefully that does not get executed between now and when I'm running my exploit. So let's compile this build. Let me look at the chat. Connor, aside from read write plus mitigation bypass, have you written exploits for other areas of Windows kernel exploitation, Win32k spooler logic bugs? I've just now started getting into Win32k exploitation. I wrote one exploit from that. But what I like to do is really, the best way to learn is look at existing POCs that are out there and try to reproduce them yourself. I'm kind of at that stage with some of the Win32k exploits. Native drivers are much more difficult to exploit than third-party drivers. And CLFS, of course, yes, definitely CLFS is a big one lately. Browser and Win32k are things I've been trying to get into recently. Okay. I'm all over the place. Take this exploit. No executable memory is what this PLC is named. So we put this here. Okay. Breakpoint hit. Perfect. Here is our ROP chain right here. And what our ROP chain is going to do, just as a proof of concept, is it is going to call, oh, here it is. Okay. It's going to call ke get current Urkel which is a wrapper for this function right here. And we're going to return that value to user mode. How can we return that to user mode? And how are we allowed to access user mode memory? Now, there is a mitigation called SMAP, supervisor mode access prevention, not execute access, where it's the same thing as SMAP whenever the code segment of the CPU is at ring 0, but you're reaching out to a ring 3 PTE. In other words, kernel mode code trying to execute user mode code. Same thing applies for user mode code trying to access data. Windows actually enables SMAP, but it does not employ it at Urkel less than 2 for legacy purposes. And there's a paper by Sarah Marr from MSRC about the feasibility of enabling SMAP on Windows that I highly recommend everyone check out. SMAP is there, but only at Urkel 2 or greater. Well, we're operating at Urkel 1 or less. You know, kernel mode code runs at 0, APCs run at 1. So, interesting thing. The function get Urkel is loaded into RAX, and we're going to jump to it, so it's going to execute it. Remember, CR8 contains the Urkel for the current process. It's going to move it into RAX and give it back to us. This is kind of a pop quiz, I guess. What would you think would be in CR8? Because kernel mode code gets executed at Urkel 0. Well, remember, right now we overrode a return address for an APC interrupt. So the Urkel is technically at 1, even though, you know, we're executing our ROP chain, because the function responsible for lowering the Urkel back down is KIAPC interrupt, which we overwrote on the return address, or excuse me, which we overwrote on the stack. So we jump into that, and then we return. Now what our ROP chain does is it does exactly what our shellcode did before. So first of all, it's going to store the result for us in user mode, because again, SMAP, not a non-issue. And then we're going to call terminate thread on our current thread using ROP. So I'm not going to step through all of that. Come back here. And we were able to get our return value in user mode. So even with HVCI enabled, we can use ROP. Oh, let me make this a little bit bigger. Even with HVCI enabled, we can still make kernel mode API calls given we have a read-write primitive, which is great. We can kind of mimic shellcode. Awesome. Just as a fun little exercise, I'm not going to step through this one completely, and this is my second to last thing. That was a POC to show we can use ROP. This is a POC to terminate the Microsoft Defender anti-malware service process using the same technique. So let me thing here. Construct ROP chain, but now we receive the PID to MSMP-eng, which is the Microsoft engine service, Microsoft anti-malware service process. And here's something that's interesting. We could use our ROP chain to open up a kernel handle calling ZW open process on privileged processes, right? So there's something in Windows called a PPL, protected process light, special kind of processes that you should be able to tamper with even as an admin, right? But from we have kernel access, so we could open up a handle, right? So we could open up, use a ROP chain, open up a handle to msmpeng.exe and terminate it, which is the process, except antivirus providers can register something called a kernel callback. And what that is essentially notification in the kernel that anytime an OS action happens. So for instance, there's one called PS create notify routine, I believe it's called. And anytime a process created, it's an array of functions that that drivers register. All of those get called to notify the drivers, hey, process was created. There's also one for object creation, which is what a handle is, an object. So what this Defender process does is if any user mode handle is opened up to it, trying to open with process all access, even from the kernel, like using a call to ZW open process, but it's a user mode handle. I'll explain the difference here in a second. The object creation callback gets in front of that. It strips the access rights and returns the handle back. So you can never open up a handle to Defender with the needed handle permissions to terminate the process. But luckily, there's a flag in the call to ZW open process, which is right here. There's a structure you have to pass in, which is an object attribute structure. There's a flag that you can specify called obj kernel handle. That denotes this handle as a kernel handle instead of a user mode handle. But the issue is that handles are stored in a per process handle table, right? So when I try to call terminate process, the Windows API, passing in the handle that's a kernel handle, terminate process is going to look in exploit.exe's handle table and say, hey, where's this handle at? Well, it's a kernel handle, so it's located in the system processes handle table, so it can't find it. This is why I explained previous mode earlier. When you corrupt previous mode on the thread calling terminate process, that tricks the system call into thinking it needs to look up the handle in the kernel handle table. So now we can pass in kernel handles and terminate them. This is less on exploitation and just more on a fun exercise, I guess you could say. Build solution. Let me clear all the breakpoints. Hopefully I'm not dragging on too long for people in the chat. Let me see this. Have you thought about targeting physical memory through device physical memory? I had great success through that to at least target VTL1. No, I have not, but that is something that looks pretty interesting. I should look at it more. I've had great success through that, at least to target VTL1. No, I have not tried that. Okay. Okay, so let's open up another CMD, and I'll zoom in on these. First of all, I kind of want to I'll just do it live. Okay. So if I do task list, that gives me the processes. If I do task list, find string, msmpeng.exe, this is the Windows Defender anti-malware service process. Again, only kernel mode can open up a handle to this and terminate it. We have a kernel exploit. This would be much easier to do in shellcode, but we have to do it in ROP. Successfully terminated. And that did not work all the way, did it? Oh, it actually did work. It respawned really quickly. Let me try that one more time. And it's terminated now. It's gone. It will start up later because of the way the service is configured. If the process dies, it goes to boot up again. But from an adversarial perspective, right, terminating that, doing your needed action you need to do, then it boots back up. But we were able to kill a privileged process using that. So that's great. And that's kind of what I mean about HVCI playing by its rules. We just reuse existing memory that already exists. It's a little more convoluted how we control the stack, et cetera, et cetera, et cetera. But now we will bring CET into the fold. Essentially, you can calculate the PTE base leak through the usual read primitive, calculate the physical. That is very interesting, actually. Calculate the read address. Interesting. Thanks, Austin, for that. All right, so this is the last thing I'm going to do, and I'm gonna have to use Windows 10 for this, Windows 11 for this, because if I look in Windows 10 and I do unassemble, KE is kernel CET enabled, X or AL happens, and a RET happens. This kind of means this is not instrumented right now for Windows 10. Because we basically say anytime this gets called, is it enabled? We say no, it's 0 or false and return because it's a Boolean. So now we're going to switch over to Windows 11. And we're going to deal with CET. And I will explain that. And this is the last demo that I have. I know I've been going on a long time, but I
so even if you turn on shadow stacks on Windows 10 with the exploit guard, it doesn't go through payload restrictions.dll then and turn that on, or or is it still off?
For user mode, potentially, yes. I
Okay,
think
yeah.
it will, because like after 1909, I think CET for user mode, yes. But for
Yep.
kernel mode CET, no. And there's not even a documented option. One of my old coworkers gave me the registry flag that they did from reverse engineering to actually enable kernel CET because it's not documented. Okay, so now we're going to go to Windows 11. So start the kernel debugging. This is the last demo that I have, so I know I've been going on for a while. Please tell me the IP didn't change. Okay. With HVCI, the DHCP happens all the time, change, which is what I like to use. Did I say HVCI? For Hyper-V VMs. And I like using Hyper-V because Hyper-V is what's required for HVCI and VBS to work, and the same infrastructure is used for Hyper-V VMs. So it's not nested VM with like VMware that has some driver that's doing all this hacky stuff. It's layer 0 hypervisor, and it's allocating from the actual root partition. It's much quicker, in my opinion, because of that. It's one less layer. Anyways, okay, full screen this. Okay, so if we come back and do this exact same thing, unt ke is kernel CET enabled. Now we have a compare to this Boolean or global variable. I don't know if it's global variable because it doesn't have G, but BB, which that's display byte 1. I can type. So right now I have kernel CET enabled on this machine. What is CET? CET is twofold. CET is Intel control enforcement technology, control flow enforcement technology, and it's twofold. You have indirect branch tracking, which looks at forwards edge calls and jumps, just like control flow guard. Then you have backwards edge, which is the more notable shadow stack. And what shadow stack does, it's basically what CFG did for return addresses. So our exploitation has relied on one of two things thus far: overriding a function pointer or overriding a return address. We switched to return addresses because kernel control flow guard stops function pointer overrides. And let me say this because I didn't mention it earlier. Kernel control flow guard is only fully implemented whenever HVCI is on. UNT guard dispatch icall. Oh, that's a pointer. Let me show you why. It was a question that was brought up earlier. So we mentioned earlier that the way CFG works is we create a bitmap or a dictionary that contains all of the known valid call targets, and we check that. This is where it's stored for kernel control flow guard, is guard icall bitmap. Now let me find the question earlier because it was asked. By E, could you use your read primitive to read the bitmap, find the address it already trusts, and overwrite that? Microsoft has actually thought about this. Now let me explain. The CFG bitmap in user mode is protected by dep or the kernel, so it's read only in user mode. So you already have to have some way to call virtual protect to change the permissions. If you can already call virtual protect, you've already bypassed CFG, and that's a non-starter to begin with. However, the kernel is the highest or the most privileged entity, right? So if you have kernel control flow guard and your threat model is you're trying to prevent an attacker that already has access to the kernel from overriding a function pointer, well, that kind of sucks because your bitmap is protected by the kernel, but you're assuming an attacker already has access to the kernel. So, that's a non-starter because an attacker could just do exactly what you said. I'm not going to override anything yet. I'm going to corrupt the bitmap. Then I'm going to do the overwrite. And there's something to stop that. But with VBS, we have a higher security boundary, which is the hypervisor. And using that same infrastructure, using the extended page tables, we now can mark Oh, that's going to be large page, isn't it? Let me try this. Yeah. Okay. Anyways, this should say it's writable. This iCall bitmap that contains all of the bits to know the dictionary essentially. But there is an extended page table entry that's managed by the hypervisor that actually says this bitmap is read-only. So using the same concept as HVCI, we protect the bitmap as read-only by the hypervisor. So when you go to try to overwrite this, even in the debugger, I have this in my blog post, it will actually give you a memory access violation because, again, even though the kernel says it's writable, the hypervisor says, no, this is a read-only. And that's how the bitmap is protected. And when you have VBS disabled, all of these routines are here for iCall for CFG, but they're no ops, essentially. They just let execution go through, except for one instruction. Test the upper bits of the address. And if it's a user mode address, kill the process. So it acts as a software SMEP that actually works better than hardware SMEP, to be quite honest. So that's that. Now with CET, we have a shadow stack. So what that means is we have a hardware protected copy of the stack. It doesn't have any parameters on it, just return addresses. And what happens is anytime a ret happens, just like CFG, we do a check now. And we look at the shadow stack, which is immutable. You cannot corrupt it because it's hardware protected. And we compare it with the real stack. And we say, hey, is the return address on the shadow stack the same as the return address on our stack, on the normal stack? If it is not, someone must have overwritten a return address and we crashed the process. So ROP is impossible now. You can't do it with CET enabled. And it uses these same concepts here. So in user mode, CET, software still has to check, right? It has to do the check to say, hey, is the shadow stack, when the compare happens? Well, the shadow stack, the code to do the compare is in the kernel. So if you have a user mode exploit, you already need access to the kernel to get around that. Well, that's a non-starter, right? Because if you have access to the kernel, you got bigger problems than bypassing CET in user mode. Same thing with kernel mode. Kernel CET relies on HVCI in order to properly work. Because again, we can protect the code that does the checks with a higher security boundary. So it's impossible to overwrite stack addresses now. And let me show you what this looks like. So I'm going to take our ROP exploit where we, let's see, is it in the video folder? Perfect. I'm going to take this exploit where we override a return address, CET enabled, and we get this fatal right here. And if we look at the analysis, kernel security check failure. A shadow stack violation has occurred due to mismatched return addresses on the call stack versus the shadow stack. I don't know if we're going to get the instruction responsible for this. So this is where our ROP chain started, right here. These may look familiar to you. That's how we were popping into RAX. And now we fast fail because we've overwritten a return address. And then when that check happens, CET kicks in and we're toast. Now, how do we get around CET? Well, I'm going to caveat this last demo with it kind of specific to your exploit target. Let me explain what I mean by that. I have a notes thing over here, so let me make sure that I don't have anything written down that I didn't want to talk about also. No, I think I've hit most of the stuff. Okay, let me view the chat real fast. How much would you say you've learned from your current work and colleagues? Because learning alone is pretty difficult. I don't know how to answer that properly, because for me, I still know that I have a lot of work to do to get where I want to be. I've only been in my current role in engineering, which is more low-level stuff, for the last 6 months. So really the first 2.5 years was I was lucky enough to be in an apartment by myself with no one, no pet, no responsibilities besides my job. And I just went crazy, I guess you could say. So in the last 6 months, you get to a point where you kind of get to the modern part of it, like this kind of stuff. And as Steve and I were talking about earlier, kind of off stream, the tribal knowledge aspect, where some of this stuff really, it's asking people questions. But really, it kind of took me probably 2 years to get to this. And then the last 6 months, I've really been able to get more pointed by asking questions of my peers. Like, you know, when you're writing code for a sensor that's operating all in kernel mode, that's running on millions of machines, you know a lot about kernel internals of how to make everything work. And so luckily I can ask questions of people of that. At what point during the boot process does HVCI kick in? Can you use your kernel exploitation to deploy a rootkit bootkit and use that to disable it? Really early, like super, super early. I have part of it in my blog, kind of following the process of how a hypercall is made to configure those VTLs, and it happens very early in the process. I don't know if you can do that. I don't think so. There are also other mitigations besides that, like secure boot and other type things that I don't know enough about, to be quite honest with you. 2 hours late. Yikes. Welcome to the party. Okay. Cool. So we know that we can't use raw with CET, right? So let me show you something absolutely glorious. I need to pull up this. So this is from my Twitter that I did a while ago when I was first learning exploitation about 2020, about 2 years ago. And in here, I bypassed kernel control flow guard by overriding an import address table function. And the reason for why I did this is because, oh goodness, okay. Import handling. Calls through the IAT should not use CFG protection. The IAT is read-only in modern images, right? So CFG, anytime, because if you actually look at an IAT call, an import address table call, that's actually an indirect call that happens through a pointer. And we'll see this in the IDA disassembly here in a second for this driver, or in the actual disassembly in WinDebug, and I'll show some things in IDA, right? Those, for performance reasons or otherwise, I'm not entirely sure, and I don't want to speak to it. When we call through the IAT, they're not checked by CFG. And why is that? Because the IAT is read-only on modern images. And that means, well, you can't corrupt the IAT because it's read-only, right? So you need a read-write primitive already in order to corrupt the IAT, to corrupt the function pointer to call into something else. HVCI actually only withholds the executable bit. It's only for execution. So the page table entries, I know we talked about that the page table entries, the extended ones, are used for this checking, right? But that would be so redundant to check the extended page table entry every time, right? So let's say that right now, and let's say I call kuser shared data. The page table entry already says this page is not executable. Why would I go check the hypervisor to make sure that they say it's also not executable? There's no point in doing that. That's a performance thing. Why would I do that when this page table entry already says it's non-executable? So we don't check the hypervisor every time, actually. A time when we would check it is when the execution bit is set, and then we verify that it's actually. That's a redundancy to check both the PTE and the extended page table entry if we already see that it's non-executable. HVCI is only used for withholding the executable bit. It actually doesn't look at these other bits. And you can actually corrupt the page table entry to mark the page as writable, and we can write to it even with HVCI enabled. So we can still corrupt the import address table to corrupt the function pointer that CFG doesn't check even with HVCI enabled and call a malicious function. Well, we also are not overriding return address on the stack. So now we're going back to our old primitive where we still need to bypass CFG, but we're able to get around CET and CFG at the same time. So let me pull up this last exploit that does this, because this is going to be driver specific. What I mean by this, you can do this with other drivers, but it's going to be specific to us. So I have this IDA. Oh, it's asking me to restore the. Oh goodness. Okay, well. Oh, it's already in use. That's why. Oh, thank goodness. I thought my thing was corrupted. Okay, I have no idea how to zoom in on IDA. Is there even a way to zoom in on IDA? Can I do this?
You mean on the screen as a whole?
Yeah, like to make the. I know I can do it here. I don't know if I can do it in.
I don't know. If you use a Windows magnifier, it crashes IDA these days. So.
Yeah. Okay. Well, everyone, if you can't read this, just trust me. Which I don't know why you would, but just trust me. Okay. So for this driver, these are all of the imported functions that are being used. So the IAT, it's a table of all the imported Windows APIs we want to call. These are all the ones that we want to use. So I picked this one. So this driver is going to call allocate contiguous memory specify cache. I do not give a crap about that function, but I want to see where it's called. So I double click on it. Oh, I can't zoom in like that either. Let's go back here. You're just going to have to trust me. This shows me a cross-reference in this function to where this is called. Call contiguous memory specify cache. Okay, great. So if this function gets called, we call into the import address table to call allocate contiguous memory verify cache, whatever. Now we want to view cross-references, list cross-references, and we can see the call happens in another function. Okay. See, it happens right here. And I want to go to the branch that calls this. So I'm going to double click here. And the way this gets called is on a jump 0 when this compare happens. Now, this is just from experience, but I know that this is an ioctl handler. So a client will send an ioctl code, and that kind of, you can think of it as a magic value almost, that the driver can register these functions that basically say, hey, if the driver is passing in this magic value of an ioctl, I want to do this action. And I know this is an ioctl from experience because look at all these compares to numbers that are the exact same, essentially. You can verify this further. I'm not going to do it by actually seeing for device IO control, the major function code where the array of functions gets registered. But an even easier way for me is if I see a function which a bunch of compares to the same number that are within the same range in a driver that gets called from driver main, I know that that's an ioctl handler. So if I come back to here, actually, because I lost where I was trying to explain that. This is the code branch responsible for this. So I know if I issue an ioctl with the code 9B0C1EC0H, I could theoretically make a call to allocate virtual memory contiguous cache or whatever the heck that function was called. Okay, perfect. Now, let me pull up the code that I have for this. kCFG. Okay. So let's see in the main function now. So what we do now is we make the IAT entry readable and writable. Again, HVCI is on, but HVCI only cares about the executable bit. And that's not a knock at HVCI. HVCI does exactly what it's intended to do, prevent unsigned shellcode execution. That's exactly what it's doing. Just with performance and other things, some things are read-only. This IAT import address table, for whatever reason, is not marked as read-only. Or excuse me, it's not marked as an extended page table entry as read-only. That performs some verification, I should say. So after we mark it as, I do it all in here, actually, in this trigger IAT call. Go to definition. So this takes an input to the PTE base. So what we do is we corrupt previous mode on our thread, just like we've been doing this whole entire time. And I calculate the PTE of the target IAT. So if I look at the driver, so if I do DPS dbutil 2 3 plus 0x2070, that's the IAT entry that calls into this. So what happens is when this call in IDA actually, or I won't go back to it now, but that call where it said CS : function name, it actually doesn't call directly into this. It calls a pointer through this. So we can overwrite this pointer just like how dispatch table 8. But again, read only right now. So we calculate the PTE that corresponds to the IAT, and we set, last time we cleared the bit, this time we set the writable bit. Then we actually override it and update it. Now this was from some reverse engineering, but this is kind of where just toying with things work. So when this ioctal call happens, there's these things that I like to call driver checks. And on your input, the driver normally checks things like, what's the length? If the length is something certain, I know I need to use, this is like, a driver probably has a structure. This driver probably has a structure similar to this that the developer sets members on. And when the ioctal happens, that structure gets parsed or messed with. And the way a lot of these work is they look at the size, right? So the size of macro can just look at this and say like, hey, I see that this driver is 48 bytes. And the driver checks after the ioctal is hit, which we'll step through, may do a check, say, hey, is the size of the input buffer 48? If it is, I know I'm dealing with the structure I need. And what happens in this driver is you can access this ioctal and it will copy user-provided parameters to the function call for allocate virtual contiguous memory with a few caveats. So let's go ahead and build this. So this is the last one. I promise if I'm boring people. Connect. And again, we've got CET enabled, kernel control flow guard, and HVCI all there. Oh, also, I guess I should show this. Here's the registry key. It's in my blog as well. Open with, choose another app, Notepad. That's the registry key for enabling kernel control flow or kernel CET shadow stacks. Under device guard, which is kind of encompassing of HVCI and all these other things. Under scenarios, add a key called kernel shadow stacks and then add a value of 0, 1 for enabled. Okay, so let's run exploit.exe. So here's the target IAT page table entry. Let me copy this down. Read only. We've seen that thus far. Go ahead and press enter. Come back here. IAT entry is now writable. Press enter to view the IAT. Okay, exact same thing. This is now a writable entry. And if I come back, oh, that's the PET. I have to work backwards. I'm not going to do that because I'm going to mess up the math. Okay, well, the entry is writable now. Okay, and why do we care? Because again, the IAT is not checked by kernel control flow guard. And we can make it writable because HVCI only cares about withholding the execute bit. Again, this is what I mean, playing within the confines of what you've been given. Okay, so press go. Sign in. Okay. Press enter to view the IAT entry located there. Okay. Oh, it's because previous mode is set to. Oh. Okay. So what I'm doing as a POC is I'm overriding the entry with X allocate pool with tag. So my goal is to be able to arbitrarily call arbitrarily a kernel mode API
that I specify. That's my first goal. My second goal is I want to control the parameters. My third goal is it would be absolutely amazing if I could get the return value back into user mode. But again, this is different because with ROP, we were able to set everything up magically ourselves. Now we have to play within the confines of the driver, because the driver is expecting a different call, and we have to see how the driver operates on that memory to say, hey, when the memory is allocated, where does it get stored at? Can we bubble that back up? I hope this lets me go through this. I mean, I can just run the exploit, run it again, but
it's interesting. In user mode, there's a control called import address table filtering, which validates that the address in the table points to the DLL that should be in where the function should reside, but it's not in kernel.
Yeah, and there's also export address filtering, which does the same thing, which that one's interesting because the way it works is a vectored exception handler is registered, a guard page is thrown in front of the export table. So when shellcode's resolving what it needs to, like the exports, like virtual alloc, whatever, guard page violation is thrown, then the exception handler checks it and then resume. So very perf heavy and very compatibility, lots of compatibility issues there. Okay, this worked luckily. So I actually didn't need that breakpoint, unless I did. Okay. All right, don't look at any of this. What happens is when previous mode is set to I'm gonna have to step through that again. When previous mode is set to 0 on the current thread, and then you try to kill the process, it's weird because the process was started in user mode, but then when you try to kill it, it's previous mode is kernel mode. So it tries to, I don't know. I actually don't know what it does, but it does something weird because of something like that, I think. Press enter to view IAT. Okay. 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 Okay, here we go. Now we want to set a breakpoint on this because, again, where did allocate contiguous virtual memory get called? It got called in this ioctl handler. And the ioctl handler, when the ioctl, which eventually results in that call, it's right here in 5.1d4. And again, I haven't rebased IDA or anything like that. So what we do now is we're going to set a breakpoint. Breakpoint on int or on dbutil 2 3 plus 0x51d4. Make sure that that's actually the right thing. Okay. Okay, we hit the breakpoint. Wow, these demos have gone very smooth today for how I thought that they were going to go. Okay. At the breakpoint, now we hit the breakpoint. Okay, so we have input now for this. So fast call calling convention. First parameter RCX, second RDX, R8, R9, right? This ioctl accepts an RCX a pointer, and if we look at that pointer, that's our input, right? So if we come back here, that's the input we specified. 1, 100, 41, this, and this. And the way I'm setting this up is, first of all, xallocate pool with tab probably isn't the best example because I can't allocate executable memory because of HVCI. I'm just using it as a proof of concept. So just from reverse engineering, here's what I would do. I get asked, so how do you get a reverse engineering? I am probably the worst person to ask about this. Here's my workflow, right? I know that this ioctl is accepting input. How did I figure that out? I just took a long buffer, set it to 41. I sent the ioctl code. And when I hit the function responsible for handling the input, I looked at the input and I saw, oh, my input has made it that far. That's great. Then what I did, I started putting them at different offsets. So offset, I did, here I put 1s, then I put 2s, then I put 3s, then I put 4s, then I put 5s, then I put 6s. Ran it again, went into the ioctl. I looked at where is my memory getting stored at. So like in this case, 141. If I come in here, that's not exactly the same order I had everything in, was it? I know my 1s are here, but 220 is right here. 100 is here. So 100 is the third thing that's there. But here I put it second. How did I figure that out? I just looked. I said, oh, I put these in. Let me look where it's going in the kernel. And then I adjusted to what the kernel was doing, right? I looked, I said, oh, my first parameter I needs to go in the RCX register or whatever. So I just looked at, okay, well, where in the input is it getting put in? I looked at it and then I adjusted. Oh, okay, 100 eventually is using R8. I know I need to put my third parameter there, etc. This needs to say RCX. Okay. So what happens here? Compare dword pointer RCX plus 0x8 with 30. And what this is actually doing is I found this out is this is the size of the buffer. How did I figure this out? Well, the first thing I tried doing is, I look at, okay, what's that POI RCX plus 0x8? So this says, hey, whatever's an RCX plus 8, dereference that, get us the contents that it's getting pointed to by, and dump the memory. There's nothing there. It's 30. I know this is from experience as well. If you look in the actual ioctl call, what do you have to supply along with your input? The size of the input. So I looked at this and I thought, okay, that could definitely be a size. It sounds reasonable in terms of size, right? Like 48 bytes is what it is in decimal. Okay, that's reasonable. Some things like that you just figure out over time when you see smaller value. Oh, that might be a size, for instance. Okay, so I knew the first thing I had to do, because right here, if my size is not 30, basically I'm done. I'm toast. None of my input will make it there. So that's the first driver check you have to look at. Okay, 30. No matter what happens, if I want this exploit to work, I need my buffer to be 30 bytes. That's the first thing we need to do. Okay. The compare happened right here. 1, then we're going to go. Okay, we're in the next one. So now, I'm not going to step through these functions. The way, if you know if it's a Windows API or a driver-specific function, is it calling through a pointer? If it's not calling through a pointer, that's a local function probably within the driver itself. So I do T, 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 till I get to the call. Fast call calling convention. I saw a couple moves here, so I know that RCX should contain my first parameter, RBX contains my second, R8 contains my third. There's my size, RBX, let's see what's there. Okay, that looks like my input buffer, and then what's an RCX? Okay, looks like probably reused memory, like this might be some mem move or something like that. Well, what I do is I do P, because I don't want to step into the call because I've already done this for brevity purposes. So this does the call and goes to the next instruction, and what should the return value be in? RAX. So I look in RAX, what's there? Okay, did any of my data get transformed? It did not here. But what I learned is through this driver is where I set 41s, it's an RCX. So that's the pool tag actually. It's where I set the 220, right? What is that set to actually? On page pool. Yeah, 220. I noticed that this first local function transformed my data. And basically, if I had all 2s here, this call happened, it obliterated the upper 32 bits and only left me with the bottom 32 bits. So those are the little things when you're reversing. Okay, I know I'm constrained now that this has to be 32 bits. And again, this happens through all of these functions. I'm not going to step through all of them because they're just transforming the data essentially. But we see this call keyword right here. I look at this. What does this point to? Sorry, I didn't copy it. Points to the IAT entry. This is where this call is happening right here. So if I go through, okay, I'm at the call. So right now, this will call X allocate pool with tag. Well, from reverse engineering, this, if I had a full keyword or 64 bits, it eventually got the upper bits were cleared. I don't know why. That's what I mean about driver checks. Sometimes you get this weird, it's like browser exploitation, almost like this is incoherent JavaScript I'm writing, but it's what I've got to do to make the thing trigger. Exact same thing here. I don't know why this driver clears the top 32 bits, but it does. And so we have to live within the constraints of that. So this is my first parameter. This says allocate on the non-page pool NX, the non-executable. We want to allocate 100 hex bytes, and we want the tag to be set to 41, 41, 41. I run pool at RAX. They should have allocated some memory and put it on the non-page pool, which is exactly what it did. And here's our chunk, AAA. We successfully called a kernel mode API with kCFG, kCET, and HVCI enabled by living within the constraints. Now, here's the issue. How do we get this bubble back up into user mode? Because we would like to store that value for an attacker. Again, this is very driver specific. This driver to the this does the mapping of memory, doesn't it? Yeah. So when this returns where we did that, I know it seems like I'm just stepping through something. So that eventually calls IO complete request. So the driver is done. And what I did was device IO control specifies an output buffer where the driver can send something back to you. Well, what I did was I put something here and I just started parsing all of the input, all of the buffer that I sent. And I sent like a 30 byte buffer. And what I found out is that what I have is padding 1. So right here, that offset in the buffer is where the return value gets stored for that X allocate pool with tag call. Again, this is just from reversing the driver itself. So I come here, I come back to my machine. And look at that. We were able to get the return value back. X allocate pool with tag, pool chunk address, that. And if we go back and verify, that's 3839. That maybe will still be there if I didn't clear. I did clear, but that's what it was. And so, yeah, that's kind of we would like to do this in shellcode. This would be so much easier just to make shellcode blob, make it executable, and boom, we're on our way. Yeah. But again, CET, HVCI, kCFG, and that's just 3 mitigations. There's a lot more as well that are enabled. So that's kind of how you play within the rule set, I guess you could say. This is a third-party driver. So again, we were lucky here because it copied our input down into the function call. That was driver specific. Don't get you wrong. But again, something to consider.
Yeah, that's awesome, man. Good work. And thank you so much for putting in the time to prepare all these demos. I know that's not a quick thing. And yeah, the demo guys, man, yeah, I'm impressed. They have not.
I know.
They were good.
I know, for kernel mode too. I only had a couple blue screens to death, and they were on purpose to show this is what's supposed to happen. So
that was awesome. I was almost going to have you to type in .crash just to make a blue screen.
Yeah.
No, but thank you so much. That was fantastic, and I know. I'm sure a lot of questions coming up and a lot of people saying definitely got a lot of preparation to do to get up to this point. But I think that was fantastic. I definitely want to have a couple streams where we do some stuff more introductory into the kernel and then kind of loop back into this again. Because that's
yes, definitely.
But that's fantastic. Yeah, I don't know what more to say other than just thank you. That's awesome to see that on Windows 11. What a cool trick to go through the import address table to get around control flow guard. So.
Yep, and I actually want to share one thing because I did this before. This is what I mean about learning, right? So I did this before. I knew about this trick. But if you look at this actual exploit, you can't read it because it's so blurry. But I actually made k-user shared data executable. Now I'm tattletaling on myself because that should not be possible with HVCI enabled. Yeah. But for kCFG to be fully enabled, you need HVCI. That's where I learned that. I thought I was bypassing CFG, but it actually wasn't fully enabled because HVCI wasn't on. And so then I thought back, oh, I did that earlier. I wonder if that still works with HVCI on, because then kernel control flow guard is fully enabled.
That's awesome.
So tattling on myself that I misunderstood back in the day.
No, that's how it works. Did Microsoft, have you told them about that technique, and have they said anything about it?
Yeah, I told Matt I mentioned it to Matt one time about bypassing, but in their mitigate, they don't have it anymore. But in their mitigation bug bounty for CFG, it's no longer on the list of valid targets. I wonder why that is. but it's not on there anymore. And one of the stipulations was you couldn't get the bug bounty if you did these things, and it says like the known limitations, and they just say it's a known limitation. So
Oh, wow. Okay.
the only thing that I could see in user mode, yes, right? Because you have to call virtual protect to mark it as writable. Well, if you could do that, you've bypassed CFG already. But in the kernel, they could probably put something in with HVCI to make it read only. But again, there's probably some compat thing, which is likely.
Yeah. Cool. Great. Well, thank you. Appreciate it. Thanks everyone for attending, and have a great weekend. And hopefully we'll have Connor on again, because that was some great material.
Yes. Thank you.
Thanks.